So the last session of today, we're delighted to have Petros Koumoutsakos from our applied math department to tell us about learning dynamics.
Okay, thank you very much for the invitation, the chance to present our work. I'm going to be talking about the learning of effective dynamics of complex systems. And this work that has been done by Han Gao, who's sitting there, and Sebastian Kaltenbach, who's sitting next to Han. So what is it that we are trying to do? We are interested in forecasting complex systems. There are some of the complex systems that everybody seems to be talking about today. And the issue about the systems is that they are taking place or they involve physics that are taking place over multiple scales. They involve chaotic dynamics. They're expensive to simulate if you try to resolve every scale. And also, there is a long-standing effort how to design fast methods that can capture and predict the system dynamics. So there's two different ways, perhaps, that you can go about that. It has been two different ways in scientific computing. One is you just take the governing equations and you try to solve them, or you try to develop reduced order models. For example, in turbulence, large eddy simulations is the name of the game. So what we have been doing in scientific computing is actually doing some of these things. So we have been performing simulations of complex flows. So this is a multi-phase flow, work of Petros Koumoutsakos. And also what is nice about the simulations, because you have the same equations taking place, you can also study different physical systems. One was crashing waves, and this is microfluidic crystals, as they are calling this arrangement of bubbles in a small device. This story of simulating systems is something that I have been doing for many, many years. So at some point, though, there is a realization that you cannot go at it alone. You cannot simulate the flow around an aircraft only with direct numerical simulation. So you have to come up with approximations. So one of the things that I did about 20 or so years ago is started looking into machine learning and trying to use machine learning for the modeling of turbulent flows. And in particular, the crucial part of turbulent flows is the near wall turbulence. So I was looking at the time at a very interesting relationship that exists between the proper orthogonal decomposition, linear PCA, and neural networks. And I was trying to argue with people that neural networks are actually outperforming the linear principal component analysis. And also the other thing that we did, which was, I think, an interesting concept, is trying to reconstruct the flow above the wall. We use information on the wall, and for the things that we don't know, we're using machine learning, and then we were getting some very interesting reconstructions of the flow. I think probably also at that time, we did not know what we were doing, so we kept adding layers until the thing started looking good. So I think this is probably one of the first times that deep neural networks have been used, at least for fluid mechanics or perhaps in other sciences. Now, to put things in perspective, you have to understand there's a community of machine learning, there's a community of fluid mechanics, which is my other home, and one of the most prominent people in fluid mechanics is Sir James Lighthill, who actually was responsible for one of the winters of AI by producing the famous Lighthill report, so you can hear him talking about AI here.
The concern tonight, however, is with the overselling of the longer-term future of computers. The scientific community has a heavy responsibility to put forward its carefully considered view of the facts to avoid the public being seriously misled. Just as the US National Academy of Sciences did in 1966 when it reported that enormous sums of money...
And this is the joke of artificial intelligence on Lighthill himself, because the closed caption does actually a very good job. And it's not that this is fake. This is actually... and of course, there's the other side of the coin, where there are people that say, who the hell is Lighthill? After all, is a researcher in fluid dynamics, where it's easy to be misled by complicated equations involving continuous variables, and non-existent solutions arise so often. So in this landscape, that's how I grew up, let's say, scientifically. And it was interesting that back in 1999, I wrote an article, Application of Machine Learning to Flow Model and Optimization, that nobody wanted to publish, except that it appeared in some research briefs at the Center for Turbulence Research. And more recently, I published another article that has thousands of citations. I'm not telling you about the citations, but I want to tell you that look at what has happened to computers over this period of time. And basically, what in the best supercomputer of the time over here would take 1 year back in 1995, it takes about 2 minutes, even a few years ago, all algorithms being the same. So this is what has made us think different. Of course, deep learning didn't happen because of my work, but perhaps one of the most important things of deep learning was the Big Bang moment, was when Krzyzewski, Susskirev, and Hinton of the Nobel Prize fame, they were able to come up with unprecedented capabilities of image recognition using neural networks, using the ImageNet. And then, of course, this led to a lot of the things that we're doing today. And then there is the argument about how do you go about solving hard problems? Well, what you have to do is to use lots of training data and a big, deep neural network, and success is the only possible outcome. Do you agree with this statement?
Counterexamples.
You have many counterexamples. Do you know who says this statement? So it's the founder of OpenAI. So do you still disagree with this statement? Yes, okay. That's fine, but that's what this guy says. And of course, there has been a very big debate whether you need data or you need first principles. And then we can distinguish problems as having first principles or having data. Engineering and physics is in one category. Life sciences, medicine have a lot of data. There are some people that have no data and no principles. This is where you find lawyers, experts, and all that. And of course, engineering is moving more and more on the data-rich regime. Now, can we marry these two opposites? So scientific computing, the tradition is expensive models based on first principles. And now we have machine learning where you have capabilities for pattern recognition. And now comes the story of the patterns and the topic of my talk. Yes, machine learning has success for pattern recognition, but then these patterns may also be present in dynamical systems. Of course, they are not stationary patterns. And then what we are looking for, since we are looking also at reduced order models, are there latent spaces of dynamical systems where there can be more interesting relationships that can be discovered instead of what first classical principles give us. And then here for latent, you can imagine that we're talking about causal, effective, predictive, whatever the metric that you are interested in. Now, so can machine learning help us identify these latent spaces? Now, time is a frontier for machine learning. And that is something that a lot of people who work on the image recognition tasks have kind of bypassed. But us in the physical sciences, we have to worry about time. So I have spent some time trying to see whether we can replace equations with machine learning. So what I will be doing, just to show you, is to show you that there are equations that they give us data. So what if I take now the data and ask my machine learning algorithms, can you predict the data that otherwise I would have gotten from the equations? So what is nice about that is that you can do benchmarking. It's not that, look at this, I do this or that, but you can have a clear benchmark because you have the truth. So I'm doing this for the Kuramoto-Shibasinski equation, and I want you to pay attention that Kuramoto-Shibasinski is one thing, but there is also a scaling factor that has to do with the chaoticity of the Kuramoto-Shibasinski. So as you see, as the L tilde is increasing, this thing becomes more fine scales. This is space, this is time, it's just a 1D equation of this kind. And then what we can do is we can go and use our usual finite differences, discretize the equation, and then we can integrate, and then that's how actually these plots have been produced. Now, what if I want to forecast this equation by taking some of the samples of my solution as data, and then give it to a neural network and ask the neural network to predict what's going to happen later. And then, of course, I can compare. There's a little twist of what I'm going to be doing. I'm not going to be doing this exercise on the full dynamics of the system. I'm going to downscale the dynamics using principal component analysis. So because of the particular neural net I was using, this particular neural net is not doing well when you have high dimensional data. So I take the high dimensional data, I downscale them, and then I will be using a part of this data in order to train my neural network. So this is my training set. I just show you roughly how much of I took in order to do the training. And then I was using long short-term memory networks, RNNs, autoregressive, and trying to predict what's happening in the latent space. So in the latent space, you see right after the training, I'm doing really well. The green line is the truth. The blue dots is what LSTMs are giving. I'm moving up the space, and you can see it's still able to hold pretty well, but at some point it's going to start to fail. And then when it fails, it's going to fail catastrophically. In fact, there is something that you need to be aware that when people talk about PDEs, you have to ask the right question. Yes, you can do the PDE, but how about doing the PDE in the chaotic regime? So I'm just going to show you the results from Koumoutsakos that here L tilde is equal to 8. The system keeps up, the neural net keeps up. The other one has a different Lyapunov exponent, and it's losing it very fast. But the interesting thing here is even when you lose it, you still remain more or less in the same manifold, but this is not the case if you have a chaotic system. So here's my claim that I believe RNNs fail to forecast chaotic systems sooner or later is another question. So we published these things over the last 7-8 years. And now the question is, are we dead? Should we just abandon machine learning, or can we do anything else with this? So here comes the story of lead. In machine learning, you always have to have a cool acronym. I don't know how cool it is, but that's what we are actually doing. So we try to combine the best of both worlds. Now, the basis of our algorithm actually is true to Yannis Kebrekidis, who came up with the idea of the equation-free framework. It's a classical multiscale algorithm where Yannis says, okay, I have a system and I can simulate it for short times. Then I can take these snapshots and I can find in a certain way some kind of a macro scale. I can downsample, I can average. And now I have some time steps in the latent or in the micro scale. So then after that, you can use, Yannis was using Euler, Runge-Kutta, and such algorithms to move into later times. And then at some point, you have to return to the micro scale. And this is a beautiful algorithm. There's a lot of great ideas. The biggest Achilles heel, no pun intended, is this. How do you go from less information to more information? So this is something that Yannis showed me about 20 years ago. And actually, what I'm going to show you next, actually, I had the answer right there, because that's what I was doing with these neural nets for turbulent flow. But it took me 20 years to understand that what you can do is you can actually go to the latent space dynamics by using encoder-decoder. So you can downscale the dynamics using an encoder and a decoder. Then, of course, you can use an RNN LSTM to advance. And then from the RNN LSTM, you go back to the decoder, and then you have to go back and forth. There is a few things that are unknown, like how long should you stay over here? We have addressed that. You can do samples of solutions in the latent space, and looking at the variation of the solutions, we get an estimate of uncertainty. But this back and forth game is this learning of effective dynamics, which I will tell you that it works, but it doesn't work very well. And I'll tell you what I mean by that. So first of all, let's look how well it works. This L tilde, L is equal to 22. For the record, it corresponds to L tilde 3.5. So it's kind of an easy system. So this is the reference solution. This is the latent dynamics that the LED is predicting. And here we never went back and forth. We just did a one shot to see what's going on. And then what you can see is that this thing and this thing are not the same. But on the other hand, if you look at the phase space, you find out that the LED has somehow sampled the right phase space as the reference solution. The thing that is vexing me and I don't like is that actually, if I change the time that I go in the micro and the macro scale, the error doesn't really go down. The speed up, yes, it's reasonable. But this is something that tells me that what I have found somehow it doesn't matter very much about how much back and forth I am going. Now, we tried it also at the flow past the cylinder. Flow past the cylinder, this is at Reynolds number of 100. And what you can see is that basically with 2 degrees of freedom, you can replace a numerical simulation. And then not only we get the vorticity field that I show you here, but also when we look at the drag, we're able to get the drag with 4%. Now, when people talk about Navier-Stokes, very often they stop at Reynolds number of 100, and they don't show you other results. I can tell you that when I do this for Reynolds number of 1,000, it does not work. I get larger errors in the drag. So the biggest problem is actually what is happening in the vicinity of the cylinder. And the autoencoders, they need to be scaled differently. But this is just to show you something that up to a certain point, this method works, but not for a long time. We applied it also in molecules, and there is the alanine dipeptide. This is an interesting exercise in the sense that the alanine dipeptide in this phase diagram occupies these different areas. So the interesting exercise was to see that if I go and I project things to one dimension, basically to something that resembles a free energy, the thing that we found is that when the LED finds this diagram of the one dimension, actually the different minima, they correspond to different minima in the full diagram. Of course, the LED does not recover the full diagram, but it has some interesting properties, and the interesting properties are here. So when you do the training, and that's actually something we are pursuing, so when you do the training, if you don't give any training data at this region, then LED is able to find data over here, but then it messes up some other domains. If you remove this thing over here, it's able to recover things in a continuity, but then it does not let it go to other areas. So what actually you use in training, it kind of affects what you're going to get in the predictions as one may expect. So all these things have been reported. So it's a method that has good and bad things. There is some other things that Sebastian and Han and other people from the group are doing. There is this interpretable learning of effective dynamics that Sebastian with a group of Mark Schonauer have worked together. But I would like to tell you something that we are really excited. Actually, this has been published. I'll show you at the end. Is about generative learning of effective dynamics. So what is generative AI that many people talk about today? So what is the idea? The idea is that if you want to summarize it, is you pose the learning as a problem of a density estimation. And then what you see is if you get some data, an image or anything else that you want, you consider this data as samples from an unknown probability distribution. And then what you do is you have to find an estimate of where this probability distribution that one sample is this one or this one. And then you have to generate new data via sampling of the Q hat. So maybe you get this picture, but then the other picture that you can get afterwards is new data can give you the girl with a pearl earring with a different scarf. So how do you do that? You're playing the game of a forward noising process that you take the initial data and then you add noise and you arrive to a completely noisy field. And then what you do in playing back is you reverse, you denoise this process and you're training a neural net based on this data that you have between these sequences. Now, there is a very nice variation of that, and the nice variation of that is that you can play the game of forward and backward. So you go forward, you generate data, you go backward, and you train a neural net to reproduce all the sequences. But now you can ask the neural net to observe an invariant of the system, a mean field, or anything else that you like. So this is guided variational diffusion model, where you decide that you have perhaps the mean value of the image should be preserved in the new probability distribution that you're learning. So we noise, and then when we do the reverse, we're using guidance. So now the question is, and the idea is, can I use as guidance the latent dynamics of my system? That's actually the generative learning of effective dynamics. I have the LED, which I can get an evolution of a latent space, can I use this latent space as guidance for learning my effective dynamics? So how does this work? There are similar ideas, if you like, that are around. And actually, I'm showing you this because this guidance, we're not going to do it only on static images. We're going to be doing it on videos. Except that the videos we have are not going to be videos that are animation videos. They're going to be videos from physics, because the physics that I showed you earlier has sequences of data that are correlated because of the physical system that you're having working. So the idea is there are diffusion models for time sequences, and now I want to incorporate them for forecasting complex physical systems. So two ideas that I'm trying to combine, three. I'm trying to combine LED with diffusion models for time sequences, plus the idea of guidance. So how does it all work? This is the GLED. What we do is we take high-dimensional data. We are downsampling them to a lower-dimensional manifold. The lower-dimensional manifold is evolved through transformers or whatever you want. And then we use diffusion models to go back out into a high-dimensional space to capture the system dynamics. So this is LED in a different color scheme, because I will show you what I consider diffusion models to be. This is the microspace. We use an encoder. We get a latent representation. This is my LSTMs, and then a decoder takes me out to the microspace. That's the classical LED, just different color scheme. And now what we do here is the following. I do microspace. Instead of an encoder-decoder, I just have a downsampler, because my decoder is going to be the diffusion model. So we view diffusion models as decoders, and then these are decoders that are implying some denoising that is conditioned on the latent dynamics of the system. And that's actually the full idea. There is one more idea that comes from Sebastian and Petros Koumoutsakos from TU Munich, that you can actually modify the gradient term that you have up there by physics. So you can incorporate physics as virtual observables in the gradient guidelines that you do. But this is basically the idea of generative learning. Diffusion models, we see them as a very fancy decoder. And actually, I would like to argue it's a very powerful decoder. The details of the implementation are here. So this is, again, we take an image, S, and then we noise it. And then this is the noising schedule that we have here. We invert the noise by through this process. And then this is the neural net now that we are training. And the input of the neural net is the latent space. So that's an important thing. When we are doing the minimization, the latent dynamics is part of the input of the neural net that we are training in order to arrive back to the original image. So now, when we are going to do forecasting, the difference now is going to be, there's no difference. Well, here I have trained my neural net. This is a neural net that receives as input the noisy state of the system and the latent dynamics. So now, when I go back, what I need to give is I need to give a noise sample, and then together with my Z, I'm going to be getting a prediction, and then I'm doing the unrolling through this process. Actually, starting here and going back to the things that we want to recover. Okay, so how this is a summary, and again, the other thing which is very important is I show you the examples only for an image, but you have to be aware that we are doing it for sequence of images, all this training, and the sequence of images, the key and important thing, they're just not random images, but they're sequences that are related by the physics of my system. So these are batches that I am training, and this actually allows for temporal coherence and to increase the temporal smoothness of the system. This is the idea of Fedon and Sebastian. So the idea is that you go into the diffusion model and into the score, and then in addition to the classical term that you have, you can introduce any other constraint, and then accordingly, the formulas that I showed you earlier, they depend only on this blue thing here. But when you are introducing also some kind of a constraint, you're getting different formulas. But this is also, I believe, a very powerful idea. How good it is? Well, let's go back and see some results. So go back to the Kuramoto-Shivasinski. Again, this is L tilde, I believe, 3.5. Am I correct? So the idea is that you can train the system, and then you're starting with different initial conditions, and then you're giving it to GLED, and then this is the corresponding DNS, and you can see that in some cases you get really very accurate representations here, and they start to diverge in these areas. But I want you to see that in the phase space, actually, GLED starts to capture the fluctuation of the system. Now, since this is L is equal to 3.5, I said to, I asked actually, Han, please give me L tilde is equal to 15, because this is where things become more chaotic. And I was very happy that Han gave this, which actually, if you follow here, it shows you the GLED, the way it is decoding and the way it is forecasting. And then you can actually see that the behavior of the system is much closer to the truth than anything that in fact we had before. So the blue lines is what we would have gotten with the previous methodologies that we had. So we seem to be carrying on for a long time, and then I think he did it even for longer times. And then what he is comparing, actually, the phase space diagrams are also quite fascinating to see what the GLED is doing and what the correct forecasting of the system is doing, and then you can compare the things one-to-one. And to the best of my knowledge, this is the longest that anybody has ever simulated at least this particular chaotic system. So I find it that it's quite exciting with this generative learning process. We took it one step further, and we did flows in a backward-facing step. So this is a step, the flow goes over here and starts tumbling. And what you're looking here is that the stringwise velocity over different times. And then this is the solution that we get with LES. This is the solution that we get with GLED. This is stringwise velocity, wall normal velocity. You see that you start to compete basically with LES. And then when we are comparing the accuracy of the method on a flow, which is quite challenging, has separation and so on, you find that LES and GLED, they give you quite accurate results. We compared with other video diffusion models for this particular flow. We didn't find them to be as accurate as GLED. And finally, we also tried it in a challenging turbulent flow. The Reynolds number is based on tau. So this is a high Reynolds number flow because it's RA tau. And then if you look at the classical LED, let's start with that. LED was not performing well at all. But now this GLED is able to capture similar results on very challenging diagnostics. And then this is comparison with different methodologies. So this has just been published in Nature Communications. Actually, today they told us they put it in the highlights of the journal. You can find all the details. And for even more details, Han and Sebastian are the people to ask. Summary of GLED, quite surprisingly for me, I never thought that it would be getting results like the results that we get for turbulent flows, and we can forecast complex systems and their statistics. This is a summary of the methodology, and since we are here, I want to say one more thing that we are doing these days. We are also trying to use algorithms to discover algorithms. This is a project that we have from DARPA together with ULU and Cengiz Pehlevan. The idea is, can I discover multi-scale algorithms? We're doing the Kalman filtering, and we try to discover wavelets from scratch. And we see it as some kind of a biological process. We have components And then you use genetic programming to combine the different components in a certain way so that you can discover at least these two algorithms, eventually learning of effective dynamics, and then every possible multi-scale algorithm. And then I think I can retire after that happily. Wishful thinking. Thank you very much, and I'll be happy to take any questions.